We've been talking at length about the binomial coefficients. And this binomial coefficient here, n choose k, literally means from the set of numbers, positive integers from 1 up to n, choose k of them. How many ways can you do that? And then our theorem is that this is how many ways. But when we look at this expression, we see, well, k factorial doesn't make sense unless k is a non-negative integer. It really has to be a non-negative integer. But up here, there's nothing that says that n has to be a non-negative integer. So to get the generalized part of the generalized binomial coefficient, what we're going to do is we're going to let r be any real number. Any real number. And in fact, you could even let r be a complex number, and this would still hold. That we get r minus 1, r minus k plus 1. This still makes sense. R choose k makes sense. So if somebody asks you what's pi choose 8, then you can make all kinds of jokes, but mathematically it still makes sense. So let's do some examples just to kind of ground this and to see why somebody might want to do this. Let's do negative 4 choose 3. How would we compute negative 4 choose 3? Again, we can't rely on the combinatorial definition because that doesn't make any sense combinatorially, but algebraically we can compute it. So let's compute it and see what happens. Minus 4 minus 1, minus 4 minus 2. That's the numerator. 3 terms on top is the easier way for me to remember it. And then I'm going to divide by 3 factorial. Now, when I'm computing something to gain insight, I don't care what the actual number is. I care what the structure of the number is. So I don't want to simplify. I want to gather my terms and not simplify them. I'd rather identify what's interesting and what's going on. So here I'm going to gather out my negative signs because I see 3 negative signs on the top. And I'm going to group those together, and I'm not going to simplify. I'll leave them as minus 1 cubed. Now what does my numerator look like? Now it's 4 times 5 times 6, and I'm dividing by 3 factorial. Well, that's interesting because I noticed that I'm missing some numbers here. If I wanted to have 6 factorial, I would need another 3 factorial. And then I would have 3 factorial down here to kind of balance that out, right? And then I'd have 3 plus 3 is 6. So actually, this is minus 1 cubed, 6 choose 3. So that's kind of fascinating. Minus 4 choose 3 is negative 6 choose 3. Let's see if that holds in general. And this is the strategy that you want to use a lot of times when you're playing with these and doing some algebraic manipulations. Do a really specific example that you can do that's small enough you can kind of do all the terms and see if you notice anything, and then try to generalize it. Now let's try to figure out what is minus n choose k. And here I'm assuming that n is a positive or non-negative integer. Like we had n was 4 in the previous example. Let's try to do the exact same manipulation. So I get minus n times minus n minus 1, blah, 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 minus n minus k plus 1, divided by k factorial. Now, it's not as obvious to me here. It still makes sense, but it's not as obvious to me that here that I want to factor out that negative sign, but it worked last time, so let's do that. There are going to be k of the negative signs that I'm going to pull out, so I get a minus 1 to the k. And now the numerator, as I saw last time, is going to be an increasing sequence. It's going to be n times n plus 1 times n plus 2, all the way up to n plus k minus 1. This is called a rising factorial, as opposed to a falling factorial, of course. And I've still got my k factorial on the bottom. And now I can see that, yeah, this is totally a binomial coefficient. It's absolutely going to turn out nice. I've got my minus 1 to the k, and what is it? It's n plus k minus 1, choose k, which isn't just a binomial coefficient. Let's think about that in terms of our last lecture. This is choosing with repetition. This is n choose k, where you're allowed to repeat. This is the donut problem. So this seemingly ridiculous algebraic contrivance that I did actually has some kind of really nice combinatorial meaning. And that's something that often happens in combinatorics. We take insight from a case that makes sense, like when r was a natural number, it made sense. We extend it to a place where a priori it doesn't make any sense, and lo and behold, everything still works. Let's do one more example. This is going to be relevant for your homework, so if you stuck around this long, good job. Pay careful attention. We are going to just figure out what is negative 1/2, choose 4. Okay, so among negative 1/2 things, choose 4 of them. That, of course, makes no sense, but we can compute this. So let's do it. Again, I'm going to follow, just write out what the formula is. -1/2, okay? -1/2 minus 1. -1/2 minus 2. -1/2 minus 3. There's my numerator. And I divide by 4 factorial. I'm just going to start doing the same simplification I did before with my negative numbers. So I'm going to pull out my negative signs. There are 4 of them. So I get -1 to the 4. And now let's see if I can simplify my terms a little bit. So I've got 1/2, and then I've got 3 halves, and then I've got 5 halves, and then I've got 7 halves. There's a distinct pattern I've noticed up top, and I'm dividing by 4 factorial. Okay, so again, let's not simplify things. We don't want to multiply things out. I'm not getting rid of that -1 to the 4. I'm going to keep it around, just so I see the structure of what I'm doing. And I'm going to pull out all those fractions, because goodness knows I don't like fractions. So on the top, I've got 1 times 3 times 5 times 7. And on the bottom, I've got 2 to the 4, and I've got 4 factorial. That's interesting. And I could stop here, but I'm not going to. What I'm going to do is I'm going to think about, hey, I don't like those odd numbers. I really wish it was just a factorial. And I'm going to use inspiration for what's on the bottom. So let me do a little aside down here. Let's observe, what is 2 to the 4 times 4 factorial, that thing that we see on the bottom? Well, it's 4 factorial is 1 times 2 times 3 times 4, right? And 2 is, to the 4 is, there's a 2, there's a 2, there's a 2, and there's a 2. And then I multiply these all together. But I could think of grouping them like this, right? Where I put one of each of these 2's with one of each term here. And then I just get all the even numbers. I get 2 times 4 times 6 times 8. That's really handy, because if I were to take those odd numbers that I have up here and interlace them with these even numbers, then I would have a nice 8 factorial. And that sounds much better to me than 1 times 3 times 5 times 7. So I'm going to multiply on the top and the bottom by this. So I'm going to get -1 to the 4. And maybe I'll emphasize how I'm doing this. 2, 4, 6, 8. And on the bottom, I'm going to put a 2 to the 4 times 4 factorial, because now we know those are the same. And I'm going to put them back in my 1, my 3, my 5, and my 7. And I had a 2 to the 4 times 4 factorial already. So now we can see this is kind of cleaning up nicely. So I'm going to combine. So I'm going to leave here. I got -1 to the 4. I've got on top an 8 factorial. On the bottom, I have 2 to the 4 times 2 to the 4, which is the same as 4 to the 4. Now I'm confused as to which 4 is which, but I think this 4 is an honest 4 and the exponent is a k. And I've got a 4 factorial, 4 factorial. That's kind of super nice. So what do I have? I have -1 to the 4, and then I have 8, choose 4. And I have a fraction here, which is 4 to the 4. So if you can kind of figure out which of these is n and which of these is k, then you'll be able to figure out what is -1/2, choose n, and get a nice formula for that that's sort of this flavor.